Good morning. I welcome you all for the today's session code conversion. So in this code conversion, we have types in code conversions like binary to gray, gray to binary, then binary to XS3, XS3 to binary, then ASCII code converters. There are so many code converters, but in our syllabus in second unit in our course we are going to discuss about only four code converters, that is binary to gray and gray to binary, vice versa. Okay, then binary BCD to XS3 and XS3 to BCD. So what is the difference between this? Is also vice versa. In general, just binary to gray, gray to binary, then BCD to XS3, XS3 to BCD, both or vice versa. Okay, if you are able to convert one conversion, like if binary to gray, you will be able to convert gray to binary very easily with the first conversion itself. So you should be clear with two conversions, any two conversions, so that it is easy for you to convert the remaining two. Okay, so as we know very well the difference between combinational and sequential. The combinational, in combinational circuits your output depends with your present inputs. In sequential circuits your output depends with your present as well as in previous with your previous outputs, right? So first we are going to convert the binary to gray. So first of all, a converter is needed to convert information. They are basically encoders and decoders. Coding is the process of translating the input form and understandable by the machine or a particular device. Coding can be used for security purpose to protect the information from stealing or interrupting. Okay, so the applications of code converters are like computers, digital electronics, VLSI devices, many devices. So there are many types of code converters, as I said. So there are numerous codes like binary, octal, hexadecimal. BCD is binary coded decimal. XS3, gray, error correcting codes, and ASCII codes. These are the different types of code converters. So first let us discuss about what is a code converter. So here I would like to say that first you should know the difference between binary to gray. You should know the difference between binary and BCD. Binary means your hexadecimal from 0 to 15, and BCD means we have to consider from 0 to 9. We should not go for that A, B, C, D, E, F conversion. Okay, so here in binary to gray, first you should know in there are two parts here, that is your analysis part and design part. In analysis part we have to start with circuit, we have to completely understand the circuit, and we have to end with truth table. But in design part we have to start with truth table and end with a logic circuit. This is the main difference between analysis and design part, right? So in code converters also we have to start with truth table and we have to end with logic circuit. See here, now we are going to convert binary to gray. That binary can be represented as B0, B1, B2, B3, and gray can be represented as G1, G2, G3, G0, G1, G2, G3. Whatever it is, the variables depends up to user convenience. Okay, so if binary means we can consider like B0, B1, B2, B3, and gray can be represented as G0, G1, G2, G3. Binary to gray means from B0, B1, B2, B3 we have to convert G0, G1, G2, G3. Okay, so for example let us take one 4 bit here, like let us take 4 bit here, like a 0 0 1 0 or all zeros, any examples. Here I have taken 1 1 1 0 1 as an example. This is your binary. From this binary we have to convert this binary into gray. Okay, so first see in this example 11101, first let me consider this 11101 as B1, B2, B3, B4, and the conversion can be G1, G2, G3, G4. Okay, so here B1, B2, B3, B4 means I should know how to what is G1, what is G2, what is G3, what is G4. So B1 means directly I can take for G1. So B1 is equal to G1. Understood? B1 is equal to G1. Right? So next what we have to implement the XOR function here. We have to implement the XOR function. So we have to find G1, G2, G3, G4. So G1 is equal to B1. What is G2 next? G2 is, we have to use XOR function here. We know very well in XOR only if both the inputs are 0, high, that is low. If both the inputs are low, your output will be low. If both the inputs are high, your output will be high. If any of your input is high, your output will be high. Understood? If any of your input is high, that is 1, your output will be 1. If both the inputs are low and if both the inputs are high, the output will be low. This is our XOR function. We have to implement our XOR function here. So G1 is directly equal to B1. And what is B2? B2 is G1 XOR G2. G1 XOR G2. Here the example we have 1, 1, 1. So 1 XOR 1. 1 XOR 1 means if both the 1 is high, your output will be 0. So automatically your B2 will be 0. Understood? Next B3. B3 is G2 XOR G3. G2 XOR G3. So what is your G2 here? 1. G3 1. So again you will get 1. Understood? Next your B3. B3 is your G3 XOR G2 XOR G3. Likewise, simultaneously next you have to XOR with your next bit, the next bit, so that you will get answer. So here G3 is equal to G1, start with G1 is equal to B1, G2 is equal to B1 XOR B2, G3 is equal to B2 XOR B3, and G4 is equal to G2 XOR G3 XOR G4. Understood? So likewise we have to convert, and this is the conversion of binary to gray. This is your binary. Since I said we are using XOR function, I have used XOR gate here. So for this completely by using K-map, we should be able to prove what is G1, G2, G3, G4. Understood? So this is the logic circuit of our binary to gray. And truth table, here we have to use our binary to gray inputs. Your binary is your inputs and gray is your output. So for an example, we have taken one bit like 1110, and for this entire 8421 code